Hey there, another brand new chapter for us. We're going to start chapter 9 right now. And in chapter 9, we're going to be working with transformations. In this video, what you're going to learn to do is to apply properties of translations and appropriate notation to translating figures in a coordinate plane. Alright, so you're going to learn properties of translations, and you're going to learn the notation that goes along with translations in order to translate and really describe translations of figures in a coordinate plane. Alright, and we'll be working with translations, and then later on in another video we'll work with what are called vectors. Okay, now a long time ago, back in chapter 4, we looked at the concept of transformations briefly when we were studying congruent figures, and we talked about how there were 4 types of transformations, 3 of which we studied then, all 4 of which we're going to study in this chapter. And those different types of transformations were translations, reflections, and rotations, as well as dilations. Now, the first 3 all had something in common, and the thing that they all had in common is that they're all isometries, which back in chapter 4 was just a word I wanted you to have heard, but now in this new chapter, isometry is a word that you need to know the definition for. And what an isometry is simply any transformation in which measurements are preserved, both lengths as well as angle measures. And below you see an example of what I mean by that. I've given you an example of an isometry. Now, while I'm explaining that, I'm also going to be reminding you of some notation that you learned way back in chapter 4 as well. For instance, you learned that whenever you have a transformation of a figure, you can note which points are images of other points by using what's called prime notation. Alright, so this point A right here got mapped to this point A prime. This is the image of this point. B prime is the image of B, and so forth. Now I'm using that word image. Remember that you called the original figure in a transformation the pre-image? And you call the resulting figure after a transformation the image. And whenever you use prime notation, it's very obvious which is the pre-image and which is the image. Now, as far as the isometry part goes, what's important here is that the image and the pre-image are congruent figures. And so all their corresponding parts are congruent. Angle A would be congruent in measure to A prime. Angle D would be congruent in measure to angle D prime. Segment AB would be congruent in length with segment A prime, B prime, and so forth. Alright, so isometries are transformations in which lengths and measures are preserved, and another way of saying it is that an isometry is a transformation in which the image is congruent to the pre-image. Now let's focus on translations in particular, alright, and what a translation is. Now, you know that a translation is simply when you take a figure in a plane, alright, P-L-A-N-E, and you shift it, basically. I'll be a little more specific than that though. Whenever you translate a figure in a coordinate plane, what you do is you translate or you shift every point in that figure the exact same direction and distance. So suppose I wanted to use this as the direction and the distance of a translation. So I'm going to slide this point all the way over to here, and let me go ahead and graph that, or well, graph, not really a graph, but you know what I mean. Let's say that point is the image of this one, and then what I want to do is I want to shift every point that exact same direction and distance. So I'm going to do a little copying here. Alright, we'll shift this point the same amount, and we'll do the same with every point going around this pentagon. Like so, and then I can go ahead and connect all those images that I just made. And you'll see that I'll end up with a figure that's congruent to the previous one. Alright, yeah, the orange figure and the red figure are congruent to one another. Now I want to talk about some properties of a translation. You know what's a slide of a certain distance and direction? Well, the geometric entity, so to speak, that would describe that distance and direction that I've represented with these arrows right here is something called a vector. And a vector looks like a ray, you remember rays, except that there's one key difference. Where if these vectors were rays, we would say they would go on forever. A vector has a definite ending point. It begins here, has an initial point just like a ray, and it goes in one direction, but it actually ends where the arrow ends. All right, so this is the entire vector, whereas if that were representing a ray, it would go on. Okay, we'll talk a lot more about vectors in the next video. That is something you're going to be learning in this section. But just wanted to show you that vectors can be used to translate, well, plane figures. All right, let's look at some of the problems that you're going to need to be familiar with in this section. We're going to go ahead and go to the coordinate plane. And I've got a problem that I want us to work on right here. We're looking at translations and what's called coordinate notation. And you see some coordinate notation right here, by the way. It says that the vertices of triangle XYZ are as follows: 3, 5, 1, -1, -3, 0. All right, I've already got those graphed over here. It says graph the figure, then graph its image after the translation. And here's the way you read this. XY is mapped to x minus 4, y plus 1. The point XY is mapped to x minus 4, y plus 1. Okay, so this notation right here tells me exactly the direction and distance in order to translate each of the vertices in this figure in order to get the image that I'm looking for. So it's telling me I take every x-coordinate from the pre-image and I subtract 4 from its x-coordinates. And then I take every y-coordinate from the pre-image and I increase that y-coordinate by 1. Now, you know that x prime, y prime, z prime are going to be the images of x, y, and z respectively. What I'd like to do is go and figure out what the coordinates are. Again, we're going to decrease each x-coordinate by 4. So we're going to do 3 minus 4, that'll give us -1. We'll do 1 minus 4, that'll give us -3. And then -3 minus 4, that'll give us -7. And then we're going to increase each y-coordinate by 1 unit. So 5 plus 1 is going to give you 6. -1 plus 1 is 0. And 0 plus 1 is 1. Now what I'm going to do is I'm going to graph the vertices of the image, and you'll be able to see that this actually was a translation. So there are the 3 images. It just happened that y prime and z had, from the pre-image, had exactly the same coordinates. And let's go ahead and connect those 3 things, and you'll see that the resulting figure is congruent to the original figure. And all that happened was that we shifted each vertex in the pre-image 4 units left and 1 unit up. 4 units left, 1 unit up. 4 units left, 1 unit up in order to create the image. All right, so very simple, right? Let's look at the same kind of problem from a different perspective. Here, I want you to write a rule for the translation, which is that coordinate notation that I was showing you. That's what the rule is going to look like. Then verify that the translation is on isometry. All right, we'll talk about that. You see 2 figures on the coordinate plane, and you can tell that the green one is the image because of the prime notation that is right there. And you can tell that the red figure is the pre-image. And basically, when we write a rule for the translation, we want to describe what do you do to every x-coordinate and y-coordinate for the points in the pre-image in order to get the points in the image. Well, let's compare the x-coordinates for each pre-image and image. You notice that this thing is just being shifted basically straight up because p prime has the same x-coordinate as p. They both have -4 for an x-coordinate. You can see that q prime has the same x-coordinate as q, and r prime has the same x-coordinate as r. So when you're not changing the x-coordinate in a translation, we'll just say x gets mapped to itself. But we are translating upwards. You can see that we got 1, 2, 3, 4, 5, 6 units up, and that happens everywhere. Here, 1, 2, 3, 4, 5, 6. Same happens with Q. Since we're just shifting the figure 6 units up, that means we're increasing every y-coordinate by 6. So this rule describes the translation that was involved. Now, how do we verify that the translation is an isometry? Well, if you recall, an isometry is a transformation in which measures are preserved or in which the pre-image and image are congruent to one another. So we're going to prove that they're congruent, and we're going to do so using the distance formula to show that each side from the image is congruent to its pre-image side length. Now, I'm not going to go through all the work for the distance formula. You ought to know that by now. Look up the formula if you don't remember it, but I will give you the results. After using the distance formula, you'll find that both PQ and P prime Q prime are 10 units long. You'll find that Q prime R prime and QR are both the square root of 29 units long. And P prime R prime as well as PR are both the square root of 37 units long. And then as far as justifying that it's an isometry, well, I just have to justify that the image and pre-image were congruent to one another. So I can say that triangle PQR is congruent to triangle P prime Q prime R prime. And that by SSS. So the translation is an isometry. At this point, you ought to have a really good idea of what a translation is and what its properties are. I just want to do one more small set of problems with you here just to make sure you understand the notation, and then we'll be done and we'll move on to the next video for this section. All right, and so here you see that coordinate notation that we're talking about, and it says we're to use the translation represented by this rule here in order to answer a couple of questions. And basically what I'm trying to teach you is if you're using this coordinate notation, how do you find the image if you know the pre-image? And how do you find the pre-image's coordinates if you know the coordinates of the image? So let's start with the first thing that I said. Well, let's figure out what the image of a point C would be located at -2, -4 if you translated it according to this rule. Well, very simply, all we have to do is take the coordinates of C and follow the rule here where we're going to subtract 1 from the x coordinate and we're going to add 4 to the y coordinate in order to get the x and y coordinate for our image, which would be C prime. And so that, of course, tells us that C prime would be at -3, 0. All right? Then it's asking in the next part, what is the pre-image of F prime, whose coordinates are 3, -1? All right, well, in this case, what I'm telling you is that if I decrease the x coordinate of a point F by 1 and I increase its y coordinate by 4, that the result is 3, -1. So that 3, -1 is going to go there. And what we're trying to figure out then is what are the values of x and y such that x minus 1 would equal 3 and y plus 4 would equal -1. I'll make two simple little equations here. X minus 1 equals 3. So that tells me that x equals 4. And then y plus 4 equals -1. So y is equal to -5. That means that the point F was the 0.45. Now another way of approaching that same problem is that this rule takes the pre-image and it translates it 1 unit left and 4 units up. So to go from the image back to the pre-image, you've got to do the opposite. You would have to go 1 unit to the right, so from 3 to 4, and then 4 units down, so from -1 down to -5. Let me put my negative sign in there. All right, great. You now know what a translation is. That's all I need for you to really know in this particular video, guys. Thanks for your attention. Good luck with all this stuff. See you next time.